Okay, the very last slide will be all of these problems. There's 15 slides, right? That you get something like that. But I'm going to go through like for each group of problems and show you what's expected. You're supposed to get out of that group, okay? And most of it, these are just copied examples from the book. I'm not going to redo it. So that was a slide 2. So you should be able to use the one-to-one property for exponentials like we just did in the quiz, right? They gave 2 examples here. Remember, when it's a one-to-one property, right, you should be able to represent both sides as powers of the same base. And they're not using tricky numbers here. I mean, it's almost always 2 or 3. I mean, you got to know the powers of 2 and 3. You know, in this case, the 9, obviously, that's 3 squared. And that's already got a base of 3. Once it says 3 squared equals 3 to the x plus 1, make an equation out of the exponents. You know, 1/2 and 8, you know, you should be thinking, okay, that'll be 2. 2 to the 3rd is 8. 2 to the negative 1 is 1/2. So be able to use one-to-one property for exponentials. That is from the first section, it's example 4, if you wanted to go look at it, right? I don't want to copy every line here. Right, you should be able to evaluate exponential functions that are in the context of a word problem. So this was an example in the book. It was actually, we did this one in class, where they gave us an equation that told us the amount of plutonium. It's actually a half-life kind of thing, right? The amount of plutonium that was still around after Chernobyl, right? And they wanted to know how much was still around in 2017, which in this problem, the 2017 correlated to t equals 31. It looks like it cut off the bottom there. You can kind of see it right there. So in 2017, t equals 31. So you put in a 31 there and just calculate, right? This is not at the point where we knew how to solve equations like that. You're not being asked to solve anything. You're just being asked to plug in for the variable and calculate, right? You know, the main thing is you can't just turn around because it's a word problem and say, well, I don't know how to do that. It's not asking you to do much. Okay, the next page, the next section was in the logarithm page, and there's going to be a few kind of true-falsy kind of questions in there that are basically getting at, you know, properties of logarithms, you know, what's a common logarithm, what's a natural logarithm, you know, the fact that logarithms and exponentials are inverses of each other, right? You need to know those properties. Just like on the last question in the quiz where you had to like simplify something if it actually meets that property right there, right? The base of the log equals the base of the exponential. So okay. So let's see if we can just answer these. The inverse of the function f of x equals a to the x is called the logarithmic function of base a. Right, inverse of exponentials, logarithms. Right, the common logarithmic function has a base of 10. The logarithmic function f of x equals ln of x is called the natural, right? Logarithmic function has a base of e, right? The inverse properties of logarithms state that log base a of a to the x equals x, and a to the log base a of x equals x. Doesn't matter the order that you put those two together, they cancel each other out. Right, the one-to-one property for natural logarithms states that if ln of x equals ln of y, then x equals y, right? And the domain of the natural logarithmic function is the set of positive real numbers. Remember, logarithms, you can't take the logarithm of a negative number. You can't take a logarithm of 0. Okay, this is converting from logarithms to exponentials and exponentials to logs, the same way that we did on the quiz, right? They actually, in these problems here, right, they give you an example right at the top. Log base 5 of 25 equals 2 is the same thing as 5 squared is 25. Do the same thing with these, right? That should be an easy problem. If we're missing this problem, then the test's not going to go well. And these would be same thing, just go the opposite way. 5 to the third equals 125. Then log base 5 of 125 equals 3. Right? These, now you got E involved. Right? Write the exponential equation in logarithmic form. ln of 1.6487 equals 1/2. Right? Use one-to-one property for logarithms. Right? Make it one log on the left equals the log of the same base on the right, and then make an equation out of what's inside. What's inside is called the argument. Okay, this is again, it's an evaluate of a logarithmic function. It's not a solve. All you have to do is plug in for the variable and calculate. Right? We did this one in class where they gave us this function that represented what they were calling the memory model, and they asked us to plug in for t equals 0, t equals 2, t equals 6. I mean, you can do that all just mindlessly in the calculator. Just plug it in for those three, write down your answer, just like they did here. Okay, use change of base formulas, right? And it's important when I'm talking about the change of base formulas. Change of base formula tells us that we can do this, right? We could take this log base 5 of 16, and because sometimes we have calculators that don't have a log base function that would let us do a log base 5, we change it to another kind of logarithm that we can do, like on front of a 83 or any of our calculators. We got log base 10 and log base E, ln. So change it to one of those. This one could be ln of 16 over ln of 5. Right? That's a change of base formula. Okay. Now, if it says rewrite it, then you rewrite it and you're done. Right? You don't have to do anything else there. It's not asking you to actually calculate this thing. Right? It's asking you to rewrite it with the change of base formula. So don't then like turn that into a decimal like that's the answer. You weren't being asked for that. And especially don't just say, well, I can do that. I can just do it with my log base function. I'm just going to give the answer. You weren't asked for the value of this thing. You were asked to rewrite it using change of base formula. Now, if you had something like one of these, then you wouldn't be able to put it in the calculator, right? If I had to rewrite this one here, that would be ln of x over ln of 2.6. And you just have to leave it like that. That's all it means. It says rewrite it. Just rewrite it, stop. Right, then we did the expand and condense, right? By expand, right, we meant to take one logarithm and break it up into many logarithms. So you could see on this first one, log base 4 of 5x to the third y, you can use product property because this 5 is multiplying x to the third, and that's multiplying y. So those products there and there become pluses, right? The product of the logarithm of a product is the sum of the logarithms of the factors. Right. Now there's one more property you can use. Once this 3 is the exponent for the entire argument of the logarithm, then you can pull that in front as the coefficient. So that 3 there, now it's here. That's an expanding. Okay. The quotient property is the one that lets you take a fraction and then that's a division, so that quotient becomes a subtraction of logarithms. Right? Divide becomes subtract. And normally, if you have a square root, you would write that like to the 1/2 power, so that you can take the 1/2 and use that as a coefficient. So look at what At this step right here, they're going to take that 1/2 and move it to the front, 1/2. So if you see a square root or a cubed root or something like that, that's what's expected. Condensing is probably the one I think we have more trouble with condensing than we do with the expanding part. But condensing is when you take the many logarithms and put them back into one. Like this one here, if I want to put that into one logarithm, I know that I'm going to use a product property because of that plus right there. But I can't do the product property yet because of the coefficients 1/2 and 3. So I do the reverse of what we just did on the last slide, take these coefficients and make them exponents, right? Make this 1/2 be the exponent of the x. Make this 3 be the exponent of x plus 1. And then you can put those two together into one logarithm, right? You can't do that as long as there's a number in front of the logarithm. And you can notice that at the same step that they did that, they changed that x to the 1/2 into a square root of x. Same thing. Right, this one is because of the subtraction, you know you're going to put it together with a quotient property. Because of that 2 in front, you're going to have to first pull that inside, like they did there. Then you put it into one fraction. Right, that's condensing. Right, then we did some solving of equations. Right, remember the steps for solving equations. Right, solving exponential equations. First step, isolate. Right, in this problem, right, to isolate the exponential, which is here, first they added 4, and then they divided by 2. Right, all that right there was isolating. Right, then from this step to this step, what are they going to do? Take the log of both sides. Which log are they going to take? Well, if the exponential is base 3, they're going to take log base 3 because of the property, right? So this is take log of each side. Okay. Then what you're left with, there may be a little more solving to do. So in this case, you have 2t minus 5, because that's what the exponent was. Add 5, divide by 2. Now, if you get down to this point here, they don't really show how they're doing this, but this log base 3 of 15 over 2 is 7.5. You could put that in the calculator. If you're using that one and it's got the log base in it, go ahead and do it. You don't have to use the change of base. I'm kind of surprised they didn't show a change of base, but they didn't. So just remember, where do you find log base in the calculator? Math, right? Go math, scroll down to the bottom. So isolate, take the log of each side, and then solve. Solve whatever's left. Those were our 3 steps for exponentials. Right? For a logarithm, the 3 steps are isolate. Okay, let's see. Here they subtracted 5. They divided by 2. Right? All of that there was isolate. Then what do we do? And I have to say, what they're showing here is not exactly what we did, but what I told you to do is convert to an exponential. Effectively, it's the same thing, but they call it exponentiate both sides. But what would be the exponential if you have ln of x equals negative 1/2? The base of the exponential is e. E to the negative 1/2 equals x. When they say exponentiate, they make this ln of x the exponent of e. They make negative 1/2 the exponent of e. And then, because of the property, when you go e to the ln, they cancel each other out. So they're getting to the same place. I think it's a little cleaner if you just convert it to an exponential. You solve it in one step. Now, there was one more step to solving a logarithmic that is not shown here. not that. Check. Why do we check our answer for logarithms more so than we would check them for exponentials? Because what? Because of extraneous, right? Because logarithms have a limited domain. You got to make sure the answer you just got would not lead to the logarithm of a negative or the logarithm of 0. So check for extraneous. Okay, what is this? Okay, then the last two are kind of really what I'm putting on here for the last two. That was the homework problem from last night, as far as the study guide goes. And what I mean by that is do a problem where it's an exponential, and they're going to give you the left-hand side, and you have to solve for the t. The constant, this 0.1129, is given, right? So you don't have to take one step to find the constant and another step to solve. Just plug in for the s. In this case, the s was 80 billion. So they plugged in the 80 billion and solved, right? It's a one-step process. Divide by, there's one thing to solve for. Divide by the 9.3, take the log of both sides, solve. So you should expect, should be able to do one where the constant's already there. And then the next one, the last one, is from 31 and 32. You did the 31. 32 is another example of the same kind of thing. Probably the best example of that for us was in the homework from last night. In fact, I don't even think that was the best. I think 23 was probably a better example of it, where we had to take two steps to find. One to find the constant b, and then the next one we were able to solve. Okay. These here will get at that. They didn't have a great example already worked out. Okay. So again, that is the entire study guide put together. And the same drill, right? You don't have to do every problem, but each one of these is asking you to do a little something different, right? So make sure you can do that thing before you move on to the next kind of problem. And you could turn it in for extra credit before the test. If you want to do a retest, then you need to have done the study guide. Show me that you prepared.